righty. Okay. So one of the things that we were talking about the other day at our committee meeting was, I don't know why this has shrunk this little box, but never mind, was how to look at some special interest groups. And one of the things that people seem to be interested in was radio astronomy. So actually in a previous life, before I started really doing a lot of astro imaging, I was actually involved in amateur radio. I still hold an amateur radio call sign, and actually in my past life I was actually a radio officer in the Navy, and so I've spent many decades being involved with radio, and over the years played with a number of aspects of radio astronomy in my hobby. And so the committee said, well, let's see if we can do something to generate some interest, look at something different. So we're going to do an introduction to radio astronomy. Now, we're not going to go into huge amounts of details. Radio astronomy is as broad and as wide as the rest of astronomy is. So this is going to be a broad brush looking at some of the different aspects of it, and more importantly, how you can get, with some basic equipment, get yourself involved in radio astronomy. And as it says in here, adventures in astronomy for rainy days, because that's the first thing about radio astronomy, is that actually radio doesn't care too much about the weather. So unlike the horrible cloudy nights we've had over the past few months, radio astronomy you can do anytime. You can do it day or night. So it's a real good one for those rainy days. Okay, so I always like to start my presentations with a quote. And this one's from Bill Murray. He said, "Whatever you do, always give 100%, unless you're donating blood." So that seems pretty reasonable to me. I don't fancy donating 100%. Cool. So what we're going to have a look at then. So we're going to have a look at what is radio astronomy. We're going to have a look at some of the brief history of radio astronomy. We're going to take a look at what our radio universe looks like, and start looking into things that we can observe. Well, of course, one of the biggest radio sources lives not quite on our doorstep, but within 8 minutes of light minutes of our planet, and that is the sun. So we're going to have a look at what kind of radio astronomy you can do with the sun. We're going to look at some of the radio astronomy around Earth, because actually our planet is a really noisy place. And I don't mean what man makes, but actual natural radio emissions. There's a ton going on around us. Then we're going to reach out a little bit further into space. We're going to look at in our solar system and look at some planetary radio astronomy. And then further still, going to have a look at how you could set up a radio telescope for deep sky observing. And I've got a couple of other simple radio astronomy experiments. These are not specifically around natural radio emissions, but they are around things like meteors and around aurora, etc., things like that. You can have a look at. And we'll have a very quick look at how we can get started, and talk about what the special interest groups for CAS are, and how we're going to set those up. And then I'll take any kind of questions at the end. Alrighty, so in a nutshell, then, radio astronomy is like a subfield of all the other astronomy genres that we do. So whether it's visual astronomy, whether it's astrophotography, or things like photometry, they've all got their own little subfields going on, and radio astronomy is just another one of those. And if you think about it, radio astronomy is just looking at a different part of our electromagnetic spectrum. So our electromagnetic spectrum is quite broad. It covers everywhere from, down in radio frequencies that we would normally associate with telecommunications, communications in our planet, all the way up into the X-ray spectrums and beyond. And looking at where did this come from? Well, we didn't really get a look at true radio astronomy until around 1933, as communications equipment and techniques developed. Just pre-war and post-war. Radar, for example, was one area where they discovered some of the astronomical phenomena that goes on around us. And 1933 was the first detection of radio waves from an astronomical object around our Milky Way, when Karl Jansky of the Bell Labs in the United States detected RF emissions coming from the Milky Way. Now, he wasn't exactly sure what was going on, but over the next decade or so, the research confirmed that actually what they were seeing was emissions from our Milky Way. And so they continued on up into the 50s and 60s, looking at radio emissions from our universe. They decided that they were able to identify radio emissions from galaxies, from stars, and then using bigger dishes, better electronics, really started to narrow down into, masers, pulsars, and quasars, and reach out into deep space. And that's really, really opened it up. Our own star as well is a huge radio source that goes on in the background to that as well. So we're actually surrounded by RF emitters, not man-made ones, but natural sources coming from thermal emissions, from magnetic fields, and from simply the emissions from certain gases as well. And this really jumped a huge leap in the 1950s with the discovery of the cosmic microwave background radiation. Now, CMBR, that theory is around the Big Bang theory, and really looking back into time. That was really made through radio astronomy and looking at the signals that they could detect around our sky. You can still detect the cosmic microwave background radiation if you basically turn on an old analog TV, and you can see that pattern on the screen of noise. What you're picking up is that noise around us, and things like turning on a radio and you can hear that hiss. We're surrounded by this, which is basically the radiation left over from the Big Bang. And radio astronomy really isn't just limited to deep sky objects either. Planets like Jupiter are massive radio sources, and using some pretty simple equipment, you can receive the noise from the gas giants, particularly Jupiter, which has a massive effect on our solar system. So that's another area that we can look at in terms of radio astronomy, and that's a pretty simple one. And more closer to home is that our own planet is also distinctly noisy in the RF spectrum, which is handy for ground-based astronomers like us under clouds. There's some fascinating stuff that goes on in our atmosphere, ionosphere, and magnetosphere, and it doesn't take a huge amount of effort to pick that up using some simple equipment. So really, things are continuing to develop in the field of radio astronomy. Over the past 50 years or so, there's been huge advances in electronics, particularly around the construction of microwave equipment. And the spin-off for these really is, telecommunications, the internet, Wi-Fi. Back in the 60s and 70s, the idea of having a mobile phone with microwave transmitters in them would have been unthought of. Particularly where at that particular time, amplifiers were 19-inch racks in big cabinets. But technology has moved on a long way since then, and now we're able to miniaturize this, get very low noise with new techniques. So it's not surprising, that some of this is spilling out into the hobby area, and you'll see some of that in this presentation. So let's have a quick think about what we've got around us for a start. So while we enjoy looking at deep sky objects with our visual telescopes, you'd be forgiven to thinking that the gap between galaxies and stars are empty, that there's nothing between them, because we can't see very much on our telescopes between objects. We just generally see blackness. But that's only what our eye is seeing. If you look at our night sky in other wavelengths, for example, particularly around the microwave frequencies, you will find the signature of a very faint background radiation. And that research, since the 1940s, really culminated in the 1960s with the development of the Big Bang Theory, which we talked about, and the detection of that cosmic microwave background radiation. And that material remaining is that long cooled and dispersed signature of that event that is scattered across our universe and across our night skies that you can't actually see with your eye, but we can detect with radio receivers. As we said, if you turn on the TV, you can still see that random pattern. And, radio is really interesting, and it still fascinates me terribly in that, between a transmitter and a receiver, there is a transfer of energy, but you can't see it, you can't feel it, unless you're very close to the transmitter and where the heating starts to heat up your body. You can certainly feel it if you touch an antenna and the transmitter is running. If it's big enough, you're going to get an RF burn. But other than that, I can stand in an empty paddock and be completely oblivious to the fact that we are surrounded by RF radiation. And that's something that absolutely fascinates me, and it doesn't take a huge amount of effort to try and capture this and then to start to analyze it. So back here in home, obviously we've got all this going on. The Milky Way is full of noise, the planets are full of noise, our own planet itself is full of noise. We can sometimes see this. So when we see lightning, for example, have you ever, as a even as a kid or even as an adult, tune the radio off channel until you can just hear that background noise, and where there are storms around and you can hear that crack of lightning? Well, what is happening is that lightning discharge, that high energy pulse, is actually creating static, which is actually random noise in the form of radio waves. And we also see it in the terms of aurora as well, which is our magnetosphere, interacting with charged particles from the sun. Again, we can't necessarily see that, but that kind of visualizes the energy that is traveling in the atmosphere around us. And it's funny because other planets around our solar system also show other similar natural events, so auroras and lightning storms have been seen on numerous other planets. And that emission of radio waves, those coming from their atmospheres as well. So it's common, that what's happening in our atmosphere is actually appearing on other planets. So it's not a dissimilar process. So this is a quick look at a very famous image. This is the map of universe and the cosmic microwave background radiation. And as we know from astronomy, some objects around our universe are traveling away from us, some are traveling towards us. And we've talked before on our lectures about Doppler, redshift and blue shift. And you can see from this image, the red and blue is basically the different directions in which material is expanding or shrinking towards us in our night skies. So it's a very famous image that was mapped out in the 70s. So shifting closer to home, then the sun is, of course, a massive noise source, and we can feel some of that energy ourselves when we stand outside on a sunny day, because infrared radiation, the things that keeps us warm on the ground, is simply a form of RF energy that is at a particular frequency. It's above what we can receive on normal radio receivers, but we see it, we feel it, on our skin when you're standing outside on a hot day. And the sun emits radio waves because of the energy, the high temperatures, but also because of the way that electrons are basically being forced in spiral motions around its own magnetic field. It's similar to some of this noise that we will hear shortly around our own planet. You can receive these really, really easily. And there's some pictures at the bottom here of a simple radio telescope for solar reception. So we've got basically what is an old car radio and a laptop that is connected to the audio output of that receiver, and a simple antenna. It's a piece of wooden pole with some aluminium, some antenna elements pointing up into the sky. And so what that's doing, it's actually listening to the background noise from the sun. When it's quiet, there's probably, you can see on that diagram on the left-hand side, on the right-hand side, which is actually from a piece of software called Radio SkyPipe. You can see that the sort of background noise is a sort of general at a general level, but then there's these little spikes, which could be small solar flares, could be also interference. Although I think where he is tuned to, he should be well out of the way of any stations. And you can see there on the right-hand side, suddenly there is these huge peaks in noise, and this will be associated with a solar flare. And certainly on shortwave radios, at the onset of a solar flare, you will hear huge rises in noise. Now, don't forget that radio waves, they're traveling at the same speed as John says, background radiation seem to have as much red as blue. Does this mean as much contraction as expansion? I guess it does, John, because one is going away from us and one is coming towards us. So I don't know about the ratio. It looks fairly even. So radio emissions, and so you basically, you can see that during a solar flare there is a massive peak in noise, which can be detected on this very, very simple system. And usually you'll hear these peaks in noise within a few minutes, because we've got 8 minutes from the sun to the earth at light speed, and radio waves don't take that long to get to us, so we see the effect very, very quickly here on the ground. Radio emissions are only one part of that as well. Obviously, there's a huge magnetic pulses, X-ray pulses, and what you will see on the ground eventually is, of course, when you get the if there is an Earth-facing flare, you get a coronal mass ejection, which then impacts on the ground here and causes aurora. Okay, so that's the sun. Very, very simple system. You don't need a huge amount of effort to look at these. The other thing that we've also been playing with, so Terry, for example, has a magnetometer. And the magnetometer is basically looking at the Earth's magnetic field and measuring that using, say, a little sensor. It's actually called a flux gate magnetometer. And when that coronal mass impact happens, the Earth's magnetic field takes a huge shove, and you will actually see compass variances as the Earth's magnetic field wobbles and gets stretched out into space. And so the magnetometer will actually register that quite sharply. So that's why aurora hunters are always looking at the magnetometers on spacecraft, like GOES 15, which will give us a few hours of warning as that's further out in space, and we can then know that there's potentially an aurora coming. But knowing that we've had a solar flare is certainly something that will help you to start predicting that. Okay, so what about our own planet then? So we look at in space, but what about on the ground here? Well, there is a ton of radio astronomy you can do with very simple receivers and very, very simple antennas. Our own planet is a really noisy place in the RF spectrum, and that's, apart from all of the radio noise that we're generating. And actually some of the stuff that we generate is actually an impact on radio astronomy. We have a ton of RF emitters, television, radio, telecommunications, Wi-Fi, mobile phones. This is why big areas around large radio astronomy telescopes like Green Bank in the States are RF quiet zones. They are actually controlling electronic and radio emitters inside those zones. And they sometimes also build these in natural hollows so it can try and shelter the antenna from all of the noise that we actually have around us. So as we said, one of the things that you could do, you can find a radio receiver, and when we've got storms around, you can actually, obviously not when the storm is right overhead, because that wouldn't be safe, but you can tune the receiver off frequency to a quiet spot between channels, and you'll hear these huge crashes of static caused by lightning. And that's one form of natural radio signal that you will hear. If you go further down the radio spectrum into the VLF area, with VLF meaning very low frequency, down into the tens of kilohertz range, it's quite quiet down there in some places once you get out of the way of switch mode power supplies and things like this. And if you've got a decent antenna and a dedicated receiver to these, you can pick up these pops and crackles from lightning, and you can receive them all the way across the globe. So, and these are called spherics. I'm not going to show you a clip of that right now, so hopefully this will play. So that was the output of a receiver, just tuned to an unoccupied frequency in the VLF range, connected to a wire antenna. And what you're hearing there is basically the crackling and pops. Smells like popcorn, but that's basically lightning. We can receive that over many, many thousands of kilometers, and as the distances from the receivers increase, some of the higher frequencies travel faster than the lower ones. There's a slight shift between the two frequencies, and that causes a ringing to the signal. So that's a slightly different sounding signal. These are called tweaks, and you'll notice that the difference in them, but they're basically the same, generated in the same way. It's just that they're further away, and some of the signal arrives before the other. So sounds like somebody hammering on a wire. It's pretty cool. It sounds like somebody, jingling a spanner on a very, very long piece of wire. But what's happening is basically you're starting to get a bit of a shift in the signal, and part of the signal is arriving sooner than the other, only by literally by milliseconds, but it's enough. So there's another natural radio emission that you will hear at VLF, and these are called whistlers. And so what is happening here is that when the lightning is emitting these static emissions, basically what's happened is that some of that signal is getting looped out along the magnetic field lines of the Earth before it then snaps back onto the ground. And so, like the tweaks, the delay is even more increased, and you find that the sound is very, very different again. And studies of these whistlers have really helped understand the link between these natural radio emissions and space physics, in our magnetosphere. So let's have a listen to what whistlers sound like. So I'll play that again. You got to really listen. They're quite faint in the background. So have a listen. See, you can hear the tone of them, going up and down as in the back of the right behind all that noise. So here we go. So that's a signal. Basically, it's lightning that is zooming out into space along the magnetosphere and then back. Okay, Stones on Frozen Ice. Yeah, it does sound a bit like that. All right, and one last VLF LF look. And so this is chorus, and this is slightly different to the others in that it's not actually generated by lightning, but it's actually generated within the magnetosphere, where energetic particles enter the magnetosphere during geomagnetic storms, and they spiral around with high energy and create another similar sounding but very different type of emission. So
Earth chorus.
That sounded like a jungle full of monkeys to me. I don't know about you. Whistlers linked to red sprites. Well, sprites definitely are the plasma that is reaching up into space. So yeah, and actually one of the interesting things is that during the early 2000s, when I lived in Europe, I was actually listening to some long distance microwave beacons from Germany into the UK, and there was a really big storm in between us. Now, it's known that microwaves can bounce off the raindrops because the raindrops are a significant wavelength at that frequency, so they actually start to scatter. But what was happening is that every time we saw a lightning flash out in the distance, we were receiving a huge increase in the signal, and from the distant transmitter. And what we actually thinking was it was actually creating a plasma tube around the lightning, which was actually creating some enhancement. So there is all sorts of funny stuff go on in our atmosphere. Okay, so that's VLF and LF. So how do you go around receiving that stuff? And what are we going on here? That should move over. Come on. I don't know why that wants to play all those again. It should.
Earth.
Huh. It's very strange. Cool. Okay, so there are a number of VLF receiver kits available on the market, and this one is actually one of the better ones. It's a very, very well-known kit. It's from a NASA space physics project to bring space physics into classrooms, and it's called the Inspire. And this is the third version, VLF Mark III. And it's designed to connect to a sort of 8 to 10 foot piece of wire and actually pick up these VLF emissions from our ionosphere. Some of the kits available on the market are not much more than a small amplifier. And in the early days of computers, when we had, sound cards, like the sound blasters, when they were actually separated from the PC, some people actually used to run very long wire antennas and actually connect them directly to the microphone input, because, of course, a good audio amplifier will have a good response range, and they could be used very, very simply. But these days, with PCs not having external sound cards, they're not as easy to get into. So they built this little receiver. Now you can put a set of headphones into this, or you can feed it into a computer. And it also has some filtering. At the bottom end of the VLF spectrum are some very, very large broadcast transmitters. Now, some of these are designed for submarine communications. And Cutler, Maine, there used to be one in Rugby. There's one out in Australia as well at Carnarvon. And they can sometimes overpower these simple receivers. So this one has some filtering in it as well. I think the cost of this was about $120, $130 US, so not too onerous. And yeah, you can basically power this with a small battery, so you don't have to mess with the power supply. And you could pretty much drag that out into the wild somewhere, away from a town, away from power lines. Set it up and have a listen for those radio emissions that I've just played you. And this particular comes as a kit, but to be honest, it was very, very well documented and very well known. So if you can handle a soldering iron and a few components and some small tools, then you could build yourself a VLF receiver. There are some other kits available on the market as well, and some ready-made ones too. So worth having a look for those. So that's pretty simple to get going on VLF. Alrighty, so what about moving over into planets then? So to go a little further out. So other than our Earth, the next easiest target to observe radio emissions from a planet is Jupiter. So radio emissions from Jupiter were first observed in the 1950s, and it was confirmed by Pioneer 10 during the flybys in 1973 that Jupiter indeed was a very, very noisy place. And there are two types of, well, in fact, three types, but two radio emissions that we are really interested in. There are wavelengths down in the shortwave spectrum with a wavelength of tens of meters, around 22.5 megahertz, which is at the top end of the shortwave band. And these radio bursts that you can hear come in kind of two two different types. L burst, which is a long long emission length of a few seconds, or these short bursts called S bursts, which you can hear. They sounded very, very similar to the static popping that you heard on the VLF band here just a minute or two ago. Then there is a whole bunch of other radio emissions, but these are actually up in the centimeter range. So they actually need some quite specialized equipment to look at them. But basically, the origin of those signals was basically the magnetic fields of Jupiter and the electrons that are spiraling around that field. So we're going to focus really on the lower frequency range in the 22.5 megahertz frequency here, and that's really, really easy to look at. So let's first off have a look and see what they actually sound like. So we'll look at the L burst first. Okay. Terry says, what antenna lengths for those VLF receivers? I think 8 to 10 feet, actually, Terry. They're not huge, and they're designed for short antennas for schools. Obviously, not everybody can put up hundreds of meters of wire. Because the frequency at say 50 kilohertz is that's many thousands of meters for you to run some wire out for, which not everybody can do. All right, so there's L bursts. You can hear those sort of rises and pulses of noise, and then we've got the S burst, which is a little different. No. I think I did the wrong one. Stand by. Okay. There we go. These are S bursts. Now, you'd be forgiven for thinking that was just a dirty connection on an antenna or somebody playing with some electrical equipment locally. But yeah, they're the two different types. And so you can find those if you've got a shortwave receiver. You can find a clear frequency at just around 22.5 megahertz, and that's where those emissions are peaking. Now, Terry has been playing with a radio receiver for Jupiter for some time, and has been listening to those. And the great thing about it is actually the wavelength at 22.5 megahertz is only a few meters. It's around 10-12 meters, and what you can do is build a very simple wire antenna, and you can put these wire antennas together with pieces of relatively cheap wire and some chocolate block electrical connectors and a bit of soldering, and you can create yourself a very nice antenna. The antennas don't need to be high off the ground. Actually, they're better if they are lower, because if they are lower to the ground, that means that the antenna tends to look up versus a normal requirement for a radio antenna, which is to look horizontally rather than up into the sky. So having it closer to the ground is actually a benefit. Now, I wonder if this is going to let me change this without playing these again. Nope. I have no idea why that is. All right, so looking at Jupiter then, so any shortwave receiver capable of 22.5 megahertz reception can be used. Some people use amateur radio receivers. They're available on on the second-hand market. They're not exactly cheap, but they're not too expensive for a fairly simple one. Some people are using now what are called software-defined radios. Now, a software-defined radio is basically all of the decoding local oscillators and all the radio stages of a normal receiver are actually done in software inside a tiny little dongle. So, and those USB dongles that are in use are pretty cheap. They're about $30 for some of these things, and they cover some fairly broad frequency ranges. And there's some really, really good ones. There are some really nasty ones. One of the ones that a lot of people go for is by a company called RTL, and I'll show you what you can do with these. But those software-defined radios with the small dipole, which is basically a small wire antenna strung up in the garden or above the lawn, will do very, very well for Jupiter radio reception. And again, there are some kits if you don't have a dedicated receiver or don't want to play with software. There is a little kit called Radio Jove, which is another NASA project receiver. It's a little more expensive, but you can buy whole kits for that, and also kits for the antenna as well. So if you're not super good with tape measures and a little bit of calculation to work out the antenna lengths, then you can buy it already made. But really, these antennas are just bits of wire, so they're quite easy to make up with some simple components. And I would really recommend, if you're really interested in receiving Jupiter's radio signals, and they can be really quite strong on the ground here, go and have a look at this site here. I'll put this presentation up on the CAS site later on, and you can have a go and look at the Radio Jove website over at NASA, which has a ton of educational material. There's some presentations in there, details of the Jove radio receiver, etc. So well worth a look. Right, okay. Let's move further out into space then, away from our planet. So of course, as we move further out into space, we are looking at much weaker signals, because distance is a tyranny for radio, and so there's also a lot to look at here that we can do as amateur astronomers. Now, obviously, objects like pulsars, for example, you need a very specific set of frequencies, receivers, amplifiers, and some fairly significantly big dish to look at those. Probably more than most of us can do in our gardens, but that won't preclude us from looking deeper into space using a home-built radio telescope. Now, many of you will have heard of the hydrogen line. And hydrogen line is radio emissions that we would see due to the energy that hydrogen atoms emits, and that's a wavelength of 21 centimeters, which is 1.4 gigahertz. And so normally a single hydrogen atom will only very rarely emit photons, but the galaxy is full of hydrogen, and a lot of this tends to clump along our Milky Way, and so we can see observable spikes in this frequency as we point a radio telescope at the Milky Way. And it's quite easy to build a small satellite TV dish style radio telescope using the same receiver that we talked about just a few minutes ago, the software-defined radio, the USB dongle. And what we can do with this actually is that you can, using what is called drift scans, is if you fix the dish in one particular direction where you know the Milky Way will cross the line of that view of that dish, then you can actually see the rise in RF radiation around 1420 megahertz. So if you take a picture of this every few minutes as the dish moves, the beam of the dish moves through the Milky Way with the rotation of the Earth, then you can actually start to see the peak and rise in the energy as it passes through the beam of the dish. And doing this, there's some interesting experiments that people have done. They have measured the size and the shape of our galaxy. And obviously the thicker areas of the galaxy have more hydrogen, and so they have a bigger spike. You can also measure the rotational speed of our galaxy by noting the Doppler shift. As the Milky Way drifts through, you will look at different parts of the Milky Way, some of which are going to be rotating towards us, some of them are actually rotating away, and you can actually note the Doppler shift. And you might think, wow, I'm not really going to see that. I'll show you on a short video here over a day how obvious that is. It's really impressive. So what do we need? You need a small satellite dish, which is, you could probably find a ton of these at the recycling shop, or if you want to buy a proper one, that you can go and buy one. You need a small low noise amplifier, which is basically a building block with in and out connectors. So the input goes to the antenna, and the output goes to the receiver, and that gives you an amplifier that will amplify the signal at 1420 megahertz, but actually not generate a huge amount of noise as well. And you need that feeding into that RTL SDR and a little bit of software. So that's how you set it up, and this is what it looks like. So this is the RTL SDR. It's literally a USB dongle with an antenna connector at one end, and you use a bit of software, which actually a lot of developers have written these applications. So you can download different ones so that they can have different features and functions, including some specifically for radio astronomy. And this upturned barbecue dish is actually a Wi-Fi antenna that is sold on Amazon for a few bucks, and it does actually look like a barbecue grill with a little radio antenna on the top of it, and basically the dish is creating an upward-looking view of the sky to the receiver, and that's just got a little bit of cable, and it's got the USB dongle just below the dish, so that the actual RF feeder connecting to the active element, which is that little blob at the top, and it's actually called a dipole, which sits above the dish. That's where the dish bounces the signal to. So it receives all of that energy from around the sky and focuses on that, very much like a parabolic dish in a mirror, for example. So the image on the right hand side here, you can see, is basically on the left hand side of that is stellarium, and that's showing the Milky Way. And on the right hand side, this is capturing a screenshot of the software defined receiver on an hourly basis as we go through. I'm just going to play this. Where to look is, you can see this sort of blue area in the middle, and it looks like there's a whole bunch of grass growing out of it. Actually, we do call it grass. And all these spikes are basically interference from Wi-Fi signals and other ground-based equipment. But you'll see there'll be a huge lump appear in the screen as the Milky Way passes through the receiver. Okay, so this is running. You can see the Milky Way, and there you can see the big spike of the Milky Way as it passes it through the antenna. And you can see the Doppler as the signal moves in frequency. up and down as the Milky Way passes through it. So I'll play that again just so you can have another look. There's the Milky Way appearing, gets very strong, obviously passing through high noise level area. And there you can see the Doppler as the frequency shift hits, as the different parts of the Milky Way pass through the beam of the antenna. That's pretty cool. That's a really, really simple bit of radio astronomy. And that radio telescope would probably cost less than a couple of $100 to actually put together. So that's a pretty simple radio telescope that you can build at home and do some real science with. And if you have a look at this picture on the left-hand side, so this is a guy who's using the same system. He's using a slightly bigger dish because obviously the bigger the dish, the more signal you're going to collect. And what he's done is basically done some drift scans of the Cygnus A complex, and he's actually mapped out the different colors are depending on how strong different areas are of the sky. And as the dishes pass through there, you can see he's actually mapped out what the cloud looks like. So that's another piece of real science you're doing with some very simple electronics. Now you can you could actually motorize that dish if you were clever and built some you're good with Meccano, then you could potentially build a little rotator to actually move that dish around and point it where you wanted it to. The other thing, you could also point this at the sun, and you will also see the same noise emissions from the sun. As you get to the sun, you'll see a general rise in noise at the hydrogen line. Alrighty, so very nice and simple. And cool. So what about some other stuff then? What else can we do with our little dongle? So one of the things that I did a huge amount of over the past years was meteor scatter. Now, there are two types of meteor scatter that we use, and one is forward scatter and one is back scatter. And what I mean by that is that we're sending out a signal to an area of the sky where a meteor may pass through. Some of the signal will be bouncing off the trail and will reach out much further from us. If you look at the image on the right hand side, the transmitter is sending a signal and it's hitting a meteor, and that signal is actually reaching out forward, almost it can be up to 2,000 kilometers away. As long as both antennas are seeing a common area of the sky at around 100 kilometers above the ground, if those two antennas can see that part of the sky, then they will be able to send and receive a signal between them. The other way is actually what we call backscatter, is that if you had say a transmitter in the North Island and a receiver on the south, those two won't generally hear each other. But if a meteor was to pass somewhere along the path between the two, then the signal will be bounced out to the meteor and back to a closer point. So there's a couple of different types, but the meteors themselves don't radiate radio waves, but they leave behind them a very ionized trail that is very good at reflecting radio signals, particularly at the VHF end of the spectrum. And these ionized paths, they can reflect VHF signals up into the thousands of kilometers, and 2,500 kilometers is sort of the maximum geometric range, which is based on the height of the meteor and the angle. Most meteors burn up around 95 to 125 kilometers above the ground, and that gives you a sort of maximum geographic range of about a couple of thousand kilometers. again, if you could imagine using your little SDR dongle and a very, very simple antenna, and if you look at the bottom image, you can see this little aluminium antenna. Would fit in the back of your car. It's just a very simple, what we call a Yagi antenna. It's a directional antenna for the VHF FM band. And using this system and using transmitters that we have on the ground for domestic radio, you can hear meteors as they pass through. And you can also, like we looked at earlier on around the Milky Way, you don't want to sit there all day counting meteors. So you can use a little bit of software to actually count these, because meteors are entering the atmosphere all the time. There's lots of random space junk up there, also entering the atmosphere, because it's not just meteors that are causing this, but also space junk as well. And actually, you may also pick up what we call aircraft scatter. If there is an aircraft replacing that meteor, then sometimes the receivers will also pick up signals reflected from the body of the aircraft, a bit like radar. So what does that sound like then? So obviously we can't hear a meteor. You can see it. If you can see it visually, you get a bright, a bright trail as the rock heats up and vaporizes, leaving that trail behind it. And this is what they sound like if you've got the antenna pointing at an area where you can see a transmitter. I'll play that again. It's a pretty short clip. And that's basically a receiver looking at a TV transmitter in the United States. And you can hear this sort of ringing and wobbly effect, and that's because of multipath. And the trails of these meteors can be, 30, 40 kilometers long. So the signal is arriving at you at different times, a bit like the tweaks that we were receiving earlier. Okay. As a ham radio operator, I pretty much took this to the extreme. So instead of us waiting for a broadcast transmitter, we were actually using a transmitter at one end and a receiver at the other, using very, very strictly controlled timings. So one end would transmit at certain times, and then the other end would receive, and then the other end transmits, and then the other end receives. So you basically are going transmit, receive in very strictly controlled time zones between the two of you. This can go on for, maybe an hour or two while, you get enough rocks to pass the information. But occasionally, you get incredibly large burns. And this was one. This is taken on the VHF band, the 2-meter band at 144 megahertz from West Melton to a friend of mine, Rex, VK7OMO, who is in Tasmania. And this is a few years ago, but you can, if you thought that little ping was good, have a listen to this big rock. So what you were hearing there was basically the data that was being transmitted. There's a message being repeated at high speed between the two stations, which is utilizing digital communications so that we can get that short message between us in the shortest, tiniest space of a reflection from a meteor. And I'll just play that first bit again. You can hear that wobbling as the meteor comes through, and certain parts of the meteor trail are more ionized than others, leading to peaks and troughs, and you get that sort of Doppler bobbling effect. And there you can see the short message between us. So that's Rex VK7MO is transmitting to me. Is basically saying a short code, which 73s means kind regards. And that was the end of our transmission that we'd been doing between us. And that keeps repeating time and time again for the whole 1 minute or 30-second period. Normally we would do 30 seconds. He would transmit for 30, I would receive for 30, then I'll transmit for 30 and he receive for 30. So anyway, that's meteor scatter. Now, what about other stuff that you can do? Well, you know, that little RTL dongle, well, you can use that for some other stuff as well. So the moon also is not a natural emitter of radio signals, but it is a very, very good reflector. And we've been using the moon as a passive reflector for you know, since the 60s really. And in Belgium, there is an amateur radio station that fires a microwave beacon at the moon. And if you can see the moon at the same time as the guy in Belgium can see the moon, then you will hear this transmitter. And it uses a very accurate timing source. It's GPS locked and has a very, very well calibrated transmitter signal. So what can you do with this? Okay, well, you knowing the timing that this thing is creating, you can calculate the lunar distance, because we know that the moon isn't at a set distance from the Earth, it varies. And you can also measure Doppler shift, which is caused by the change in orbital velocity. And even to a point where the signal that is bounced off the surface, the moon's surface is full of craters and mountains and holes, and isn't a nice flat mirrored surface. And as the signal is bouncing off the moon, it changes in phase as it comes back to the Earth, and we can hear fading on that signal, which is actually called libration fading. And so using that simple beacon and your little RTL receiver and a small dish, you can do more analysis of what's happening on the moon in terms of where the moon is, how far away it is it moving towards us, going away, and what you're actually bouncing off on the moon's surface. So the beacon is actually called, its call sign is Oscar November 0 Echo Mike Echo. EME is an amateur term for Earth Moon Earth, and it transmits on 1296 megahertz. And it doesn't take a very big antenna to actually hear this thing. And this is what the beacon looks like when it's being received on the ground by a very, very simple piece of equipment. This is basically a bit of bent aluminium, and it creates a parabolic dish. And it has a little antenna at the focus. And again, you just feed this into that little RTL receiver, and you tune around looking for the signal. Now, I thought I had put a copy of what that looked like in there, and I seem to have lost the link. So what I'll do is I will put the link into this. So when you get the presentation on the CAS site, download it and have a listen to that. But basically, you're looking for a very weak Morse code signal on a specific frequency. But as the moon is coming towards us and then moving away, as it rises and as it moves through our northern point through its meridian and then sets, the frequency will vary by some kilohertz, by quite a lot of frequency actually, as the signal is, it's like the old police car passing you in the street, and we get the Doppler effect. So on one side of the moon's path, it will be a positive Doppler, and then it will reach 0, and then the Doppler shift will start to move the other way. So you can also use that Doppler shift to measure where the meridian is as well, and when it's reaching meridian. This is also all great, but how do you how do you get started? Well, obviously, you've got to have an interest in radio and looking at some of this stuff. The good thing is that you don't need to spend a fortune. Those little RTL SDR receivers, they're about $30 US. Most of the receiver kits are around $100, and most of the software for these things are free in some form. Only the more complex pro versions of software cost money, and then they're only usually a few dollars. So the best thing to do is to start on that VLF and LF end of the spectrum. You only need simple wire antennas, and you can make that from lengths of wire you can find at Bunnings, and some chocolate block connectors. These are the little plastic blocks with the screw terminals in the top of them. Learn some basic radio techniques. Some of this stuff, particularly at the microwave frequencies, you do need to be a little bit careful with plugs and connectors, but the great thing is that the Wi-Fi market has created a mass of dishes and cables that you can buy off the shelf, and pretty much you could put one of these together without even lifting a soldering iron, which is pretty impressive. Check out Trade Me. Have a look at eBay. There's always surplus equipment on there. Amazon is particularly good for some of this stuff, and I've included some links at like the RTL site. You can actually go on to Amazon and buy those receivers. And if you have a look on Trade Me, there's a radio communications section in the under electronics, and you can find a lot of equipment in there that will help you. Check out the resource page. I've got a resource page at the end of the presentation as well. But I would suggest focus on a particular area and explore that. Get some experience. If you've never played with radio before, don't be daunted by it. It's not a particularly difficult subject. Ask. Terry's been doing a lot of this. Rob is also has been involved with radio in his professional life and his pastimes. Myself, and I'm sure there's a few other closet radio enthusiasts amongst us as well. And have a look into the new CAS special interest groups. So what are the interest groups? Well, one of the things that we've been trying to do is to generate more interest in some of the subspecializations, and we're going to be creating some of these special interest groups. And we actually want you as members to actually be running these things and engaging with them. But certainly the radio astronomy one, Terry and I will kick this off. And we're very happy to help you. So if you want to build a receiver for Jupiter reception, then give us a shout. If you're interested in doing anything around meteors or microwaves or VLF reception, just shout. I've still got some gear and certainly got things like soldering irons and some more specialized equipment that I can get access to if we need anything. And Terry's got a Jupiter radio receiver. I'm sure he would happily demonstrate that to people at some point. And if anybody is interested in doing a club project, so for example, the Jove radio receiver, we could build one of those and put the audio up onto our webpage or along with some radio SkyPipe pictures, then let us know. And it's really down to you guys to decide what you want to get into. But the committee is committed to engaging and helping encourage some of the special interest groups, and there'll be some more special interest groups created as well for different areas. So some resources there. So I've included the links for SARA, which is the Society of Amateur Radio Astronomers. There is some great stuff on their website around very, very simple meteor detection, VLF receivers, and hydrogen line radio telescopes. the NASA-inspired VLF receiver, and the RTL SDR dongles. There's details in the International Meteor Organization, which has also got some radio observation sections, NASA's Radio Jove project, and the radio SkyPipe. Right. That is pretty much it. I'm quite happy to, if I can find the screen again. Oop, where's it all gone? Right. Let's see if I can turn screen sharing off. Ah, where have it all gone?
Just go to the top of your screen and a little window will appear and you can stop sharing.
Yep, it's not, it's gone.
Now just put your mouse up to the top of your screen.
Yeah.
And it'll...
Nope, disappeared. Huh. Where's that gone? Oh, it's on my other screen. Ha!
There we go. Ah, very good. Oh, that was a fascinating talk there, Simon. Yeah.
I did say I had a ton of this stuff tucked away. I thought, oh, it was actually sort of it was harder to actually keep it down in time length because there's an awful lot of stuff going on that I didn't cover, like the the magnetometers and how that relates to the coronal mass impacts and the reception of solar flares. So yeah, ton of stuff, lots and lots to do.
Yeah, no, absolutely heaps of stuff. And like you say, I've also done a bit of radio myself, but never quite done the radio astronomy thing. I did actually have a dish at one point, about a 1.5 meter dish that I was always planning on doing something with, and then I moved house and had to get rid of it. So, but yeah, no, this is a bit more inspiring. I do have one of those little RTL software dongles and
there you go.
software. So yeah, they're pretty cheap on Trade Me. They're a dime a dozen. So and easy to use. You just sort of plug them in and download the software, and away you go. Yeah. There's heaps of stuff you can do with those. So yeah, no, there's heaps of really cool stuff there, and I know the Jupiter radio that Terry's been doing is fascinating stuff there, and I've probably heard it myself listening around on the shortwave bands with the amateur radio stuff, but probably not identified it. So I should look out for it. In fact, I've got there we go. It's there we go. It's showing you. That's yep.
Oh, that little 817. Yep.
A little 817 radio there, nice little portable one, and hook a wire.
Yeah, I've certainly heard that noise on the 15 meter band, and I never really put two and two together until much later in years, and went, yeah, that's what that is.
I'm probably the same there, and I'm sure I've heard they kind of sound vaguely familiar, but never really looked for them properly. So well worth looking. Yeah, no, some fascinating stuff there, and with the hydrogen line stuff as well. That sounds pretty easy with the RTLs and the little dishes. So yeah, I quite like the idea of scanning the sky. That's quite neat. So letting the Earth be your rotator.
Yeah, yeah,
it's quite a cheap one.
Yeah, the great thing is that using that same little RTL software-defined radio dongle, you can do so much with that. Whether it's looking at VLF and LF, or whether it's the shortwave looking at Jupiter, or VHF meteor scatter receiver, or up into the hydrogen line. So one little dongle is an incredibly flexible little beast. And it would be easy for us to find a satellite TV dish and build a hydrogen line receiver and do some scans getting one of those dongles. So if anybody's interested in having a go at that, then I'm definitely happy to help out. I do have a 5 meter dish in my store, which would make a very, very good hydrogen line receiver, but it's a fairly significant piece. It's on a mount that came off a small crane. So it actually turned a very large dish, a 10-meter dish, but the dish was aluminium and got damaged with wind. But the 5-meter dish is a solid aluminium one. But if anybody's interested in that, you don't need such a big dish. You can actually create a simple parabolic dish actually using some bamboo and some string. Actually, if you get a center point, you can actually make a stressed dish. So you can create the parabolic shape using bamboo canes and string, and then lay some mesh as the petals in the bottom. So if you're good with number 8 wire or wire fencing anyway, you can quite easily make a dish up, and at that frequency it doesn't have to be a perfectly parabolic shape. So yeah.
Yes, the 1/8 wave is quite a small. It's not too big, is it? 1/8 wave of 21.
Yeah, a tenth of a wavelength normally, which is at 23 centimeters is a couple of centimeters. So yeah, it's not too bad.
All right.
Does anybody have any questions? It's a bit hard doing that. And, anybody got any questions?
Yeah, just the chap with, I think you had a 1.9 meter dish looking at Cygnus complex. What sort of, with a larger dish, do you get a better resolution?
Well, you receive more signal. You look at as the dish gets bigger, then it's like a telescope. As the focal length extends, then you look at a very smaller field of view, and that's the same with a radio parabolic dish. As the dish gets bigger, the actual beam width of the dish gets smaller, so you can focus on smaller areas. So actually, for Milky Way, actually probably the small dish is probably better because you've got a wider field. Whereas if you're looking at specifics, like that guy was looking at Cygnus A, then he probably steered in the general direction of Cygnus, knowing that it would pass through the beam of the dish over some hours. But yeah, the other thing is as well is that you as you go larger, you will reach a physical limit that you can actually build and keep it in one piece. So
how hard would it be to do for amateurs to do interferometry?
Yeah, some people are doing that. So they stations on different parts of the globe are doing long baseline interferometry using these particular small setups. So the challenge of that, of course, is timing and being very accurate in terms of time recording. But these days with GPS and that kind of helps. But there's certainly been collaborating across the globe on them.
Just a comment about the Jupiter radio. I haven't got it running at the moment. I took the antenna down because it got in the way of the washing. I'm quite keen to actually install it at the observatory. We've got a heap of computers out there. We can dedicate one of them to Radio Skypipe. There's another piece of program called Jupiter Radio, which actually predicts when Io is going to be in a propitious place and so on. And all it needs really is 2 or 3 people just to get enthusiastic, and we can put up an antenna out the back and should be up and going.
Yeah, I'll definitely give you a hand with that as well. But yeah, it'd be lovely to see a few other people getting involved in it as well. And you pick up some tips and then you can build one at home. So easy to copy.
Yeah, I think it's one of these things that if you can get it sort of live on the web, or even able to download it to sort of in blocks or whatever, then it's something that that people can listen to in their own time, and you know, you get the good ones coming through, and obviously the more people who are listening, then the more chance we got of hearing stuff. So
well, if we really get into it, we can actually, there are some different software-defined radios that are actually designed for interconnectivity. So you can actually jump onto the web and actually connect to the receiver, and it will only stream data when you're actually connected to it. So we could certainly have a look at one of those. But initially, there's no reason why we couldn't get it up and have a look at you know, some audio channels for it. Sounds a good idea, Terry.
Yeah, no, it sounds like a fantastic idea. Yeah, well, of course, as Simon's mentioned, that's just one of the interest groups that we're trying to set up. We are trying to get basically anybody who's got any kind of interest in something. You know, just put your hand up as let it known that that you're interested in that, and other people can chat to you about it. So you know, you can let people know on the forums if you're interested. And you know, we used to have a list of contacts of people with an interest in particular things. So if anybody was interested in finding out a bit more about that, or joining it, or collaborating with projects, then they knew who to contact, which is kind of part of the point. But yeah, there's all sorts of things. You know, so obviously aurora watching, meteor storms, you know, radio astronomy. Obviously, we got that interest going on. There's a bit of scientific stuff. I'm into checking asteroids. There's spectroscopy. There's all sorts of other stuff there, scientific-wise, occultations. John, of course, is busy doing a lot of science stuff with ZV scope. And then, of course, there's lots of visual observing as well. So we can have visual observing programs and things like that if people are interested in doing that on some of the telescopes out there. We could have programs set up for the different telescopes and things. So yeah, it's all about getting people keen to come together and do this stuff. It's a bit self-driven, and that you know, it's not something that you know, we're happy to kind of help sort of get things moving, but really want to hand it over to enthusiasts to keep the ball rolling and make it grow. So yeah, so definitely, if you're interested in anything related to astronomy, let it know and let others know, and maybe there's a few others like minds out there that can make things happen. So yeah, cool.
Great thing about radio astronomy is we can do this on cloudy days. We don't need to. We can actually do some without worrying about oh, can I see the sky or not tonight? Yeah.
Yeah. Okay. Did you have something, Malcolm?
Oh yeah. Well, it's pretty a bit primitive. I've got this high gain receiver here. If you can see it or not.
Oh yeah.
Oh, what you got there? Wow, that's nice, Malcolm.
Some years ago, in Australia, they were going to build a new stereo radio telescope. So the old receivers from the old telescope, they were selling off. So I got this for $20 in the late 1980s, and I gave one to the CAS as well, but I don't know what happened to it. But I've actually got the circuit diagram here for it.
Oh, right.
Circuit diagram here for it too.
Oh, we'll have a look at that when they went on one of the members meetings, or you can do it, get to drag it along. We'll have a look and see what we can do with it.
Okay.
Very good.
Thanks. Yeah.
Have a look around CAS. I have no idea whether that's in the. Never seen anything that looks like that.
Yeah, I don't know what happened to it. I did inquire about it once after I came, because I was living in Australia for 20 years, and when I came back in 2003, I inquired about it, but no one seemed to know anything about it. But don't know what happened to it. But, Would
It
have
may
been,
well have been a victim of one
would
of
have
our
been hittable with
cleanups.
this one.
Oh yeah, yeah. By the way, those little RTL SDRs, I also used one of those in Germany to and a small dish to pick up signals from the Mars Reconnaissance Orbiter as well. And that was also interesting because you can also, we were detecting the Doppler shift as MRO was heading into a Mars orbit. So you could actually detect the Doppler change. And actually one of the things around those SDRs, if you look at some of the footage from some of the Mars probes entering Mars atmosphere, quite often they will have on the screen behind them or somewhere, they will actually be looking at the Doppler shift from the signal as it enters the atmosphere and slows down as this huge Doppler shift, knowing that they've actually been captured by the gravitational field of the planet. So those little SDRs are they're quite useful.
Mm. And closer to home, of course, there's quite a few things going to the moon at the moment. So
yeah,
probably pick up some of the satellites going to the moon. I know one of the one of the landers that went there a little while ago. It might have been the Israeli one that crashed, and there was a bunch of guys, I think, in Germany who had a big telescope pointed at the moon. That's spacecraft, and they tracked the whole Doppler shift of the spacecraft as it went in on its landing, and they could pick the point where it did a somersault and crashed. They could actually see it on the trace before anybody announced anything. So
yeah,
cool.
plenty going on. So those little once you've got the basic building bricks, it's really, you know, plugging into to different antennas or amplifiers and checking out different signals. But once you've got the control of it and you've got the basic building bricks of the receiver, then you can do all sorts of stuff. There's a ton of stuff floating around with radio signals on. Oh, Gabrielle's out in the outside setting up.
Yeah.
I'm glad you could see it. It was too windy here.
Yeah, it's pretty windy all right out there. It was last time I saw.
Yeah. What's it doing at the moment? Let's have a look what it's doing. I'm going to check my weather station. I'm on the wrong. I can't check it. I'm on the wrong network.
20 knots of wind at our place at the moment.
Oh, it's been horrendous.
I nearly got blown over up in the foothills today.
All right.
Yeah, it's been pretty horrific. So, is there any other questions before I wrap it up?
That was very interesting, Simon. I really enjoyed that. Thank you very much for that. That was
a bit of
awesome.
science, a bit of to do.
Yep, thanks very much, Simon. I can always count on you and a few others if I'm ever stuck for a speaker. So, yeah, thank you once again. It's really, really good.
Yeah, you're welcome.
Thanks very much, Simon.
Oh,
that was great.
Thanks
Thanks a lot. It's really good. Yeah.
Thanks, Simon.
All righty.
Okay, see you later, everybody.
I think we're probably done.
We're all done.
Yeah.
And
Thanks
for
everyone.
attending.
Yeah,
Thanks
thanks
for the
everyone.
talk.
Catch you later.
Thanks, all.
Thanks.
See you later.
Thank you.
Take
Here
care.
we go.